Okay, welcome back. We are starting the second part of this talk, and now I'm going to present ClapAuth. From the name, what does it mean? It means authentication using clapping as a gesture. Okay, so clapping is a widely used action. We used to applaud someone, for example. We do clapping, no? So idea is to use this clapping as a biometric modality to authenticate to something. Now, one thing I would like to say here, it's fully unobtrusive. This is a buzzword that I would like to use here. What do you mean by unobtrusiveness? Do you know this? Unobtrusive. What does it mean, unobtrusive? So it's implicit. When I say implicit means it's very, very hard for an attacker to know which authentication mechanism is implemented in the phone, in your smartwatch. So it's unobtrusive. For one-shot logins to smartwatches. Okay, this solution has two applications. Number one application is for device unlocking. So you have your smartwatch here and you want to unlock your smartwatch for any reason. You have to do this 2 seconds only and you will be authenticated. This is one. Another application is accessing the secure facility. So the idea to use this mechanism works this way. For example, if we need to access this building, like here, for example, at Univis Faculty of Computer Science, we are required to bring our card, this token, for example, to access this building. Now, the point is, when you reach the building, you can clap only for 2 seconds. This data collected from the smartwatch sensors is sent via mobile network, of course, encrypted to the server that is inside this building. It requires only like 2 seconds of your data, and then it takes 1 second, within 1 second, it authenticates, it decides whether this data that it has collected is coming from the legitimate person or not. So once you are authenticated, this decision is sent to you on your watch. You are authenticated, number one, and to the door that this person should be allowed to enter. So this is how this system is going to work in order to access the secure facility. The claim is this system also doesn't require any additional hardware. Hardware is the same, accelerometer and the gyroscope. They are sufficient enough for us. So the proposed scheme authenticates users based on the analysis of the captured arm movements you make while clapping. So, approach, for example, you see here, you have a watch here. Probably this watch needs to be worn in your natural hand. So if you are right-hander, this watch should be in your right hand. If you are left-hander, it should be in your right. So you did this gesture, for example, this data, for example, it's captured using the accelerometer and gyroscope as sensors. Then you do here feature extraction from accelerometer, from gyroscope. Okay, you extracted those features, those statistic features, mean, median, standard deviation, kurtosis, cosine similarity between two vectors, absolute difference between two vectors. These are the simple statistical features that we have. So you extract the features from accelerometer and gyroscope, and then those features you concatenated them at feature fusion level, for example. So you concatenated accelerometer and gyroscope features, and then you applied feature selection here. Because 60 features, 30 features I was extracting from accelerometer, 30 from gyroscope, all of them 60. So when I, for example, if the same accuracy I can get with 10 features, it's computationally less expensive, right? So idea is to remove those redundant features, which could be done in this module, and then the template formation with those selected features you save here and in the database, and here again, then for example, you do the matching. So this green line shows you the training way procedure, and this red line shows you the testing phase, right? So for this experiments, you are required, for example, to do this enrollment supervised manner just for 300 seconds of data and 3 different actions, okay? 3 different body postures. Then you will be able to test it. So for this data set initially, if I could show you the data set also. So this, for example, we downloaded the data. We started from here actually. This is the main starting point. So this wisdom smartphone and smartwatch activity biometric data set contains data set of 18 different activities. I saw this clapping also here. But the point was this clapping has till now has been used for gesture recognition purposes, not for authentication purposes mainly. Okay. So idea is here is to use those clapping gestures, for example, to see if we can authenticate users based on this. So, yeah, so here, for example, they had 51 users. I downloaded the data from there. Sensory readings at 20 hertz. This was the frequency, 20 hertz, 20 samples per second, you could say. 18 activities in sitting, standing, walking, running, and while drinking the soup, they have collected context level data. Clapping, raw, and they have shared with us, the raw data as well as their transform data. So they have also performed this feature extraction process by themselves and have shared this data with us as ARFF files. Okay, these ARFF files, they are attributes, like something, they are actually used for VECA, training and testing in VECA toolbox. So if you see here, for example, these are the feature list and these are the activity codes. They are from A to R. Okay, so this one 18 activities. So one of the activities that is R probably we use for clapping. And the features are simple, X, Y, Z tuples. Okay, then you average, you compute the mean of X, mean of Y, mean of Z, standard deviation, okay, and absolute difference, variance, standard deviation. These are the statistical features they have already used. Now, authentication here, for example, if you remember, for device unlocking, because this decision needs to be made on the smartwatch, right? So for device unlocking, we are using one class classification, because the classifier needs to be trained only on the user's data, only this owner or the legitimate user. So we use this Gaussian distribution density classifier, this artificial neural network, which is MLP, autoencoder, for example, KNN, simple k-nearest neighbor classifier, and for accessing secure facility, because this building, for example, has to accommodate, let's say, 50 persons, 100 persons maybe, right? So this is a multi-class classification problem. So here, the server, the classifier that is residing on the server has to be trained on the data of all the persons who could actually access this building, right? And then when the testing comes, during the testing process, you will provide a unique ID. You will claim that you are Buriro, right? And the server has to perform this one-to-one match. This query sample with the samples of Buriro only, because he is claiming to be Buriro, right? And this way, it has to return me my identity. So this is a n-class classification problem. Now, because this activity, this clapping data, it was collected only for 3 minutes. And the frequency was you saw 20 samples per second. So you see, we had only 3,600 values. So out of those values, for example, we had to get only 18 samples per user. Very limited data, right? But good enough to start more analysis, right? So here, for example, training on first 50 samples. This is also another contribution that I want to say here. People normally also perform cross-validation here. Okay, and upon cross-validation, most of the time, the results of cross-validation, they are higher normally. So the point is, it's technically fine, but from smartphone authentication scenario, this is not realistic, because initial samples, for example, they are not balanced enough. So initial 5 or 10 samples, it's very difficult to get authenticated, because they are very, very different, unless your behavior becomes stable. Right? So here, for example, this setting gives you more realistic scenario, more realistic scenario. So I'm training the classifier on first unstable samples, 9 of them, 50% of them, and 4 for validation. Why I used validation? Because I had to perform this feature selection, okay, and I didn't want to use the test data to perform this feature selection. So this test data remains unseen by the classifier for all the decisions. At the end, when I'm 100% sure of the features, of the parameters, then I use this testing data to get a final testing accuracy. And train and test remains the same for both scenarios. Train set and test set remains the same, okay? So for multi-class classification scenario, for example, 9 multiplied by 50, 450 samples were used for training, right? And testing also, like, if you multiply this 5 multiplied by, for example, 9, 5 multiplied by 50, 250 samples were used for testing. So without any parameter optimization, without any feature selection, these are the results. For one class classification, this classifier, Gaussian density classifier, it was giving us only 50% accuracy. It was not that accurate. But with KNN, artificial neural network, simple artificial neural network, we were able to get 70.8%. This is accuracy, not true acceptance rate, not false acceptance rate, okay? So KNN is 76. But for N-class classification, we were already reaching somehow 90.7, which is already very, very good based on the number of samples of training. 9, only 9 per user. So feature selection. Here in this process, for example, I didn't use any already implemented techniques. So here what I do, I did it manually. I call it sequential forward feature selection scheme. So how it works, what I do, for example, I have all these 3 classifiers. I have this training data of all the users. What I do, for example, I find individually the best performing feature. So for example, I train one by one. There were like 60 features, for example. I train each classifier on each individual feature. Training and testing remains the same, okay? And I find the best classifier, best feature, for example. For example, here, let's say, with just one feature, okay, here, the GTD accuracy was like more than 80% with just one feature. And for this red line here, for example, this one is ANN, it was like 78 point something. And for KNN, it was here. Now, you were able to find the best feature, which is very, very accurate. And then you have to find the next best feature. Not individual, but in terms of 2s, in terms of 3s, in terms of 4s. So this one is the best first feature. Then let me find the best second feature. And I combine 2 features together and see the accuracy, if it increases or not. So idea is to see how long this accuracy improves and at what point it drops. So with this, for example, approach, this GTD, with just first 2 features, it already reached this highest accuracy of 85-86%. And for KNN, it kept on increasing. It kept on increasing like 25, 26 features. So I had to stop at 27 features because it started to drop. So here, for example, you see here for these 2 classifiers, these 2 blue lines, for example, these 2 features, they performed very well. Accelerometer cosine similarity between X and Y vectors and accelerometer's average mean of this X vector. So for N-class classification approach, I use this CFS subset evaluator. This is a standard approach in Weka for multi-class classification. I use this. Now the question is the results, for example, on the selected features, different selected features for one class and for N-class classification problem. You see here ANN yielded 63.27 accuracy, true accept rate, and here false accept rate is 7.06. I have not included here false reject rate and true reject rate because they could be computed from 1 minus. If you want to compute false reject rate, you can minus 100 minus 63, 70, 37, just to avoid any redundancy. Okay. So I wanted to show you here this true accept rate and false accept rate. And this is the accuracy. Okay. So if you compare them in terms of accuracy, KNN is better. If you compare them in terms of true accept rate, KNN is better. But KNN has more false accept rate as well. Okay, so this is one, and there is a significant difference between them. So I had to compromise on something, because the two accept rate is higher, I went after. For n-class classification problem, you see here KNN, it reached 96.5%. It's already a good start. So KNN had only 0.22% fast accept rate. What does this mean? So it means like less than, for example, every 100th attempt, less than a could get falsely accepted. So these are actually very, very good results. Now the point is 50 users, just 18 samples, training samples, someone can doubt. So these results could be biased. So again, just to check the scalability. What do I mean by scalability? It means probably if after some time 10 more users comes in, 20 more users comes in, what will happen? So what we did, for example, we divided these datasets into 10 random users, 20 random users, 30 random users, 40 random users, just to see, for example, if these results vary. Okay, so normally for limited number of users, the accuracy is higher. When the number of users increase, the accuracy drops. Normally in multi-class classification scenario, this happens. But for our analysis, for example, luckily the accuracy remains very, very close. So it's perfectly fine. So it's the system, this solution is scalable as well. Even if you keep increasing number of users, this system will ensure to authenticate very, very effectively. Now, this this process that the experiments that I conducted, they were conducted on a limited data set, 3 minutes of activity collected by someone else. I didn't know how they collected. It is not clear very much. So it's not good to draw a conclusion. I didn't even submit this paper, even if the results are good. So what I'm considering to do, for example, I am considering to collect the data again, okay, on my own terms and conditions, for example, 2 seconds, because these samples, they were computed after 10 seconds each. And 10 seconds, I cannot ask you to keep clapping to 10 seconds to authenticate your watch, no? So this time we have to be, yes, Johannes, we have to reduce this time, just 2 seconds is acceptable, 3 seconds is acceptable. So this is the application that we have managed to develop with my student here. And here you see, it replicates the exact scenario. So you have to first sign up for some service, for example. The sign up requires you to do this clapping for 300 seconds. Not all together, but 100 seconds in sitting, 100 seconds in standing, 100 seconds in walking. Then what we do, for example, we have divided this. So what I have done, he is also doing this. What I have done is like, I will show you also practically how it works. So what I have done is like, after 2 seconds of data, I have sampled this data. I have generated 50 samples, for example, from sitting, 50 from standing, 50 from walking. So altogether, I have 150 samples, let's say. Here, from 150 samples, what I do, I take first 75 as training, next 25 as validation, then last 50 as testing. This is how it works. For n-class classification, I will show you also how based on the data he has already managed to collect. He has already managed to collect data of 13 users, but in order to draw a concrete conclusion, we are expecting actually to have at least 30 users. So on 13 users of data, most of the classifiers, they are giving me more than 95% accuracy. Would you believe that? So this actually makes us curious to collect more data and see if this data is biased to some factor or some reason, for example. I would request you all to participate to this experiment. Now, this is our ongoing work. So still, it's a proof of the concept. It's ongoing work. We are actually planning to finalize this proof of the concept application, and based on our findings, this was just one experiment. Now he is doing another experiment. Okay, then we will develop a concrete final application based on our finding, which classifier worked well, which features were worked well, which time window was good, 2 seconds, 3 seconds, 4 seconds. And then we will test it in real time and we will see security analysis, performance analysis, usability analysis. Then we will start writing this paper. Okay. Any question? No? Any question? Anyone wants to see the demo? Is the demo ready? Yes. Is it ready?
Yes, it's ready.
Okay. You can simulate the scenario there. For example, you could sit there. You can collect data. Whoever comes to you, for example. So in the meantime, for example, yes.
Should we wait?
Okay, we can wait. We can wait. We can collect data at that. So, if there is no question at all till now, I would like to show you some hands-on. How this clapping I did. How? Please correct me if I'm wrong. I'm showing you my source code. I'm not hiding anything from it. Okay? So, no question. Okay. So for this analysis, for example, we could exploit Python, we could exploit Java, we could exploit MATLAB, we could exploit Weka, whatever you would like to. But for MATLAB, for example, because they have a dedicated toolbox for one class classification, I have preferred this MATLAB. So you need to install, if you have MATLAB installed, you have to have these two tools, PR tools, this pattern recognition tool, and DD tool. Okay. So just to show you, for example, what is this PR tool? 30, you could download this from here. 37 steps. This one. It's a well-known toolbox developed by the researchers from TU Delft. So for novelty detection in MATLAB, they use it. Now, for example, just a refresher. I'm not saying you don't know about this, but just a refresher. So the data looks like this, right? So you have rows, you have columns. Rows means you have observations. Columns, you have features, right? So, and the last column or the first column could be your labels, the true labels, right? So this one, for example, or this two is your label. Okay, here. Okay, so for example, could you see this code? So here, this gen.b, you just have to download these two tools and you just have to set path. You have to just show this path to your MATLAB, that's it. Now, for example, if you run this, so what does this mean? Means generate data of 100 points each for two classes, A and B, and divide this data into two sets. This is how this classification is done. So when we run it, we have this A, okay, and now in order to, we have like two classes here, A and B, which have 100 samples each, but it's just two-dimensional data, just to show you how it was. So I'm dividing this into training and testing, because this 0.5, for example, okay, yeah, 50% of it I'm using it for training, 50% of it I'm using at testing. So means training will have 100 samples total from 50 users from A, 50 samples from B. Test also 50 samples from A, 50 samples from B. So you divide this, for example, and just a quick view how it looks like. So your data should look like this. Is it, you are able to see it, Kevin? Okay, so you see here, we have some samples from this red color and some from blue. Now, my question from you is, which classifier do you think would be good for this? Because normally we cannot try blindly any classifier that we have. What we do, for example, we see the data, how it looks like, which classifier is going to work well on this, right? So, just looking at this data, what do you think, which classifier is going to work? Work well, of course. Kevin, which classifier do you think should be good here? This one, this one. Yeah. These red, for example, these blue. You have to say, because if you are training a binary classifier here, this binary classifier's job will be just to differentiate between the two classes, create a line, a boundary between these two, just to separate these two classes, right? Yes. So here, which classifier, which binary classifier do you think, if we need to separate these two classifiers, is more useful, will be more useful?
So for vector machine.
Bravo. Why? Why?
Because you can delimit.
Very good point. So the point is, if you classify these classifiers, they are mainly classified in two parts. One, you can classify them based on their linearity. So most of the classifiers, they are linear in nature. Okay, and others non-linear classifier, because the data is non-linear. Because the data is non-linear, it's not easily separable. We have to use some complex classifier. Very good. So now, for example, just to show you an example, if I use here a linear classifier, you could find these classifiers in their manual as well. I will share with you as well. So, for example, this LDC, what is this LDC? Linear discriminant classifier. Fisher is also a classifier. Then logistic regression is a classifier. Support vector machines with linear kernel, they are linear classifiers. I trained them. I trained also non-linear classifiers as well. And now I'm training. Here I defined them, and now I'm training. I'm training all the classifiers, let's see. So they are, if you have noted, they are, I'm training them only on the train set. This TRN means training set, right? So they are trained only on the train set. And now just to show you, for example, if I plot a decision boundary for this linear classifier, LDC, this looks like this separation, this classifier boundary is a linear one, right? Now you see here, some of the samples from this red, for example, they are falsely classified as blue, this one especially. And these red ones also, they are falsely classified. Right? So you can compute false accept rate, false reject rate exactly the way we have discussed. So you take a positive class, let's say for example, I'm taking this red class. This samples from this red class, how many samples are rejected? So means how many samples of red class are in the blue side? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, probably 12. So this is false rejection of this red line, red classifier, red class, okay? And false acceptance is this 1, 2, 3, 4, 5. Right? Clear? Yes. Any question? Okay, so if we try, I close this. I try another classifier, for example, with black line, plot C, second two, this one is the other classifier. Again, very similar. So maybe one or two will false reject rate or false accept rate will be decreased a bit, but overall, this is not going to, these linear classifiers are not going to solve this problem, trust me. So what we are supposed to do, if you just see all of them, they are similar. So you see all of them, yes.
Okay, so like
linear classifier is not going to solve it.
Okay, that's exactly my question, but is that not, like, do we need to run it to tell? Because visually you can tell that a linear classifier may not even...
Exactly, I could tell, but it would be better if we compute also the error rates, just to see. It will add a lot of value to your observation. So for example, when we are applying the non-linear classifier, so this first classifier that we have is QDC, quadratic discriminant analysis. It works somehow like this. It's not a linear classifier, so it has drawn a boundary, but this boundary is not good enough. Okay, so then for example, other classifier we have is KNN. Yeah, here for example. Now, we should be able to see two classifiers. You see how good is this KNN? This black line, sorry. So you see, now count the false rejection of this red class for this KNN classifier, just one. Only this, right? And for false acceptance, there are 1, 2, three, this one, 3. So only 3. That's why this is a good classifier for us. But if we keep doing it yes?
That good classifier is very specific to the data though. So maybe you have a problem with the generalization.
Yeah, again, the classifiers are supposed to be, they are data driven actually. So they are depending on the data.
So maybe if it's one of the problems with finding the classifier is that you have very peculiar, like the one you have just, the one with the...
Exactly. It depends. No. It depends, Dr. Reza. It depends which type of data you have. If this data is linearly separable, there is no need to use advanced, complex classifier. If this data is not linearly separable, you need to have, somehow.
Oh, yes, I agree. But the one, I don't know how, I didn't see how you plot the other.
Sorry.
The one nonlinear one. It seems to me,
This one.
Look at there, it's very, very peculiar to the data.
Yes, you are right. The KNN classifier, normally it remembers things that, okay, I have a neighbor here, I have a neighbor here. It's not a good learner, I know.
Okay, so that was the...
It does overfitting, yes. Yes, it does overfitting.
Isn't there a risk of overfitting?
Sorry?
That's the question, right?
Yeah, this classifier does this overfitting. You are right.
So the big problem is that many other classifiers are like projection of the linear. So for example, the supervised machine are projection with a nonlinear function of a linear classifier.
Yeah.
And so these might be representing very well the classification or not. This one really is.
True.
This is very, very peculiar. And
True.
one of the problems we have is certainly to balance, to trade off between finding one or finding the one that is not too overfitting. So it's like reusable generalizable.
Yeah, this classifier is doing overfitting, 100%.
Yeah,
I can prove it. I can prove it. But that's why, for example, the other classifiers like random forest, like tree classifiers, they are better at this. They are good at this. So, for example, if you see tree classifier, if it's readable, or I should run it again. This tree is a very, very good classifier, or random forest, for example. So if I run this, and just this R. Yeah, this is good classifier. But it still has some. If you take this positive class as reference, this red one, for example, it still has higher false reject rate and higher false accept rate, but it's a good learner. It is learning. KNN is not learning. It's just memorizing. Okay, he's my neighbor, he's my neighbor, he's my neighbor. So this is training we are doing only on the train set. You can compare it now on the testing if you want.
But also in this case, would be, okay, it does separate classes, but it's not continuous. So in the sense that you have two disconnected, let's say, lines that for the classifier, which in some sense is not really wanted, right?
These are rule-based classes. In rule-based classification, madam, you can have multiple boundaries.
Yes.
Yeah. So this is how these binary classifiers they work. They have just to separate between the two classes, okay, based on their function that they are using, linear or non-linear, for example, or rule-based or quadratic, It depends. When we select classifiers, we always visualize the data, how this data looks like. We plot different scatter plots and see, for example, how the data looks like. If the data is already linearly separable, there is no need to use these advanced classifiers. If not, then yes, you need to think. Okay, so now, for example, I close this. The classifiers are trained. Now you need to compute the errors. Training error, or apparent error, for example, now if you see, the training error of this KNN classifier will be really close to 0. You will see, because you have seen it overfitting now. So, and now I'm computing this classification error on testing. 8 classifiers we are using. And now you should be able to see here. The training error of LTC is 20%. And for KNN, TREE is 0, and RBSVC, this is a radial based support vector machine. It's 0.08, 0.08. No, KNN is 0.08, not 0 exactly. It's there because there were 3 samples. So now, for example, what we do, we also print the labels, the training labels, for example. We got these training labels from the training set, and now we estimate which classifier, for example, performed well. Tree classifier, you see, it has 0.00, this one. Yeah, 0.00 training error. So I want to, just to avoid wastage of time, I'm estimating the labels of this classifier only, the training labels, okay? And if you want to see the differences in the label, you should be able to see here, for example, all the A labels, because it has training error of 0, all the labels are correctly estimated. A means A. Correct label was A, estimated label is also A, right? But for the testing data, for example, now, so now we are working on the testing data. So the same classifier on test set works like this. So if you see scatter test, I have plotted test data only, and on test data, I have plotted this classification. For this one, for example, I need to compute the testing accuracy now. For testing accuracy also, let's see for all of them, sorry. And TREE was the best classifier on training data, but on test data, let's see how much it gets. So TREE is still probably the second best classifier with 16% misclassification. So it means the accuracy is 84%. 84% of the samples were correctly classified, 16% samples they are mistakenly classified, misclassified, right? Now again, if you see the labels here, you should be able to compare those labels, the estimated labels and the true labels. Lab test, I did. Okay, I need to get these label tests here. So yeah, so you see here, for example, this where I have pointed out, it was actually B, but it is now estimated as A. This is an error. Okay. Also, like confusion matrix is also important. So we always plot confusion matrix to see how many false acceptance, false rejections are there. Anyone who has any problem in reading this confusion matrix? No? Okay, perfect. Okay, so for the testing data, this confusion metric of this classifier is this. So you see 43 samples of class A, they got correct. This diagonal means they are correct classifications. So 43 of them, they were correctly classified as A, 7 got rejected mistakenly, and 9 of class B, they were accepted mistakenly, false accept rate, and this is the true rejection rate. Okay. Also, like the ROC curves that I showed you, we also report somehow these ROC curves as well. So you see here, this is not ROC curves, I'm really sorry. These are DET curves because I wanted to show you false reject rate versus false accept rate. So these are DET curves. Also, I had to compute EER as well, equal error rate. So I plotted this. But if you just do this 1 minus false reject rate, it will be ROC curves. Okay, so here, for example, if you read this, 20 is the EER. So you see on X and Y, they are the same values. I don't know if it is readable. 20, it's written 0.20. So this was all binary class classification because binary class classifiers are robust. We all know they are robust because they just have to separate between the two classes. But problem is one class classification, you know. Now, I'm deleting this data. I'm generating another data set. For example, here, I have A, which is data, and for two classes, and I'm using one as the target class. So I said, if I'm Buriro, my target class is Buriro. Okay, so this is how it works. And B is the test data, which contains the data of Buriro, also data of others. So if you see this data, for example, you have this data, and if you want to plot, for example, a 2D plot, you should be able to see data like this. So this is the training data, okay, of only me. If you want to see the test data also, for example, you should be able to see here if you insert here B. So this is now test data. These blue lines, for example, blue samples, they belong to Buriro. Red samples, they are attacker samples. Okay, so now, for example, we need to train the classifiers. I have chosen KNNTD, for example, and as a classifier for one class classification. Let's see how it draws the boundary. Do you see the boundary? So if we, not on this, for example, if we train this on A and show it on the training data like this, for example, and we here plot this decision boundary. Yeah, this is how it looks like on the training data. Now, anything in between this boundary will be marked as correctly classified by that classifier, because this classifier is being trained only on one class data. That is positive. Okay.
So is this the same classifier that you showed previously?
That was binary class version of it. Now this is a one class classification, one class classifier. So you see the difference. It has drawn a boundary only on one class data. There are no classes available here. So when we train this also, there is also a SVDD one class classifier. So SVDD draws a black line like this, for example, and anything in between this will be marked as the user A. So if here, for example, also you could plot the testing data, and on testing data you could see, for example, like how it looks like. So again, the same concept, confusion matrix. If we need to plot the confusion matrix, now no need to plot the confusion matrix for training. We are directly plotting it for testing. So in the testing, you should be able to see this. For KNN, because it was the accurate classifier, 48 samples, they are correctly classified. Okay, only this one class training was done only on the user of one class only, A, let's say. Only one of his sample got rejected. 6 samples are mistakenly accepted, and 45 they are truly rejected. So confusion matrix is very, very clear. And if we want to plot now, for example, this ROC curve, we should be able to see this. So ROC curves is this, if you can read this. So this ROC curves now says, for example, here, if you are here, it means your x is 0.02. At the false classification of 2 means false accept rate. Outlier accepted means false accept rate. So false accept rate of 0.2, if you are agree, the true accept rate will be 0.88%, which is good. So here from the ROC curves, we also compare the performance of these classifiers. So here SVDD is not working at all. So this KNN classifier is good for me. I think the basics is now clear, right?
Yes.
So now let's jump into ClapAuth. So for ClapAuth, for example, the data that I am using now is the data that I showed you from the paper, okay? So first I would show you this data. And now, for example, for all 50 users, because in the paper they claim 51 users, but for one user the data was missing, the file was not there. So we had to use 50 users data. And on different data, for example, classifiers like 4 I have used. So you should be able to see now the process running. It will take like 2 minutes, for example, to compute for all 50 users. It is training of one class classifiers, testing one class classifiers, computing the confusion matrix, everything, ROC curves, everything. Any question?
Yes. I have one question. Depending on the number of the user on which you train the model, how common is to get collision, meaning that users are recognized as different users are recognized as the same one?
As the same user.
I imagine that more users you add to the system, more likely it is to happen.
It didn't happen. If you see the slide of scalability, it didn't happen actually. It didn't happen actually. It was because this data was collected in a very, very nice and controlled way, for example, and the data was so different from each person that it was classified very, very accurately. But this happens. I told you that there exist some sheeps. This is Doddington Zoo. For example, I am a sheep. What does it mean by sheep? It means I have a lot of intra-class variations. Within myself, I cannot sign exactly the same way I used to sign 10 years ago or now, for example. All my samples will be different. So if there are a lot of variations in my own samples, someone could exploit that variation and attack me. Though that category will be called wolves. I hope I answered you.
Yes, thank you.
48, 49, 49, 49, 49, 49, and 50, finally. Okay, so here, for example, now, these are the results that I showed you, but I didn't use LOFD at that time. LOFD, you see, this true acceptance rate is 83, averaged over all 50 users. True reject rate is just 16, which is 1 minus this true accept rate. False accept rate is 25, which is okay, keeping in mind that the data is limited, keeping in mind that we have not done any feature selection, we have not done any parameter optimization, like how many neighbors are we using, So it is a good start, right? Agree?
Yes.
So 87, with KNN we got 87, but false accept rate is a bit high, you see here, 35.53. 87 is good true accept rate, 12.98 is false reject rate, but still, we have to perform feature selection just to see. So for feature selection, you could try, for example, different approaches, but what I have done here, for example, these 8 or 9, you see EMG, CFS, no, sorry, these are for others. CFS, this one, CAE, attribute evaluator, GRAE, gain ratio attribute evaluator. These are different attribute evaluator that I have used, and using these as the schemes, I found these features. Okay, but it's not time to repeat them here. Now the point is, I'm stopping this one. I'm again clearing this one, and now I'm training these systems with the data that Kevin has collected now, just to show you how it works. For one class classification, for example, Mr. Kevin has collected data from 13 users. Now, if you could read this, we are using the data of 2 seconds here. Just 2 seconds. 2 seconds means like if the frequency of collecting data is 50 samples per second, it means you will have 100 values from each 2 seconds window. And here, so I read this data. It has 82 features. Okay. Yeah, sorry. He has managed to extract 82 features from each, and in 83rd feature there is a label. Okay. So but the users are just 13. I'm sorry to say. We have to manage, we have to increase this number. So for this 13 users, for example, if I run the same experiment and see how long it takes for 13 users, already 11, 12, 13 done. So for 13 users, for device unlocking, one class classification scenario, we are reaching this with this LOFD classifier 94.10 true accept with all features. I have not done any feature selection at the moment. And just 5% false reject rate, 26% false accept rate, and 73. These results are already good. We have to do this feature selection also. But the point is, more number of users, for example, would increase a lot, would add a lot of value to this research. Okay, for KNN also, you see, they are 93%, so it is already very, very good. But we need to somehow address the problem of false accept rate. Okay. How many of you have used classification learner? You have used classification learner, very good. So at this moment, what I have shown you the results analysis of one class classification that I'm using, for example, for clapping, right? Now we are doing multi-class classification, replicating the scenario of accessing a building. Okay, so for example, I'm opening a new session here. I'm clearing everything. Okay, so here I'm reading that training file that I read. Here train. So classification learner here, it's asking me like if I use cross validation of 5-fold, for example, to get the training accuracy, for example, just to see, to finalize the models, I'm using this. I could use hold on method or a resubstitution method as well, but I'm using this. So you took first 82 features as predictors, last column as your classes, okay? So this is the multi-class classification problem. You see, you have 13 number of users and you have 82 features. Now, here you see also 82 features. For example, here I would like to use all the classifiers. So this tool, for example, is equipped with at least 43, 44 classifiers. So idea is to, let's say, use all of them, for example, to train, and let's see what is the training accuracy. It will not take long, to be honest. Some of the classifiers, which are like ANN, for example, wide area ANN, or QDC SVM, for example, it could take a bit longer, but I don't think they will take longer. So you see, tree classifier already trained and got this validation accuracy of 84%. For a multi-class classification scenario. And this linear discriminant, you see 95.4. Kevin, you also have to note this. 95.4, this linear discriminant, probably because we have to implement this classifier to run on the server as well. Okay, and wow, you see SVM linear 96.9. SVM quadratic also 96.9. So the data set that Kevin has collected is better as compared to the data set that they collected in Wisdom Lab. So why I can comment that this data set is collected in a better way? Because this data set was collected in a controlled environment here in the university faculty building, and he was sitting in front of the participant, for example, to do this data collection himself. That's why. So you see here, if we count all the classifiers that are giving us more than 90% accuracy, how many of them? So there are like up to 2.31 classifiers. So you see here, 84, no, 1. 2.4 gives us more than 95 validation accuracy. Knife base 2, SVM linear 3, SVM quadratic 4, SVM cubic 5, medium Gaussian 6, Gaussian coarse 7, KNN 8, 9, 10 KNN cosine, 11, plenty of them. I've lost my patience to count. There are many. So the point is, if all of these classifiers, so they are classifying these samples correctly, it means that classifiers are not overfitting. They are not biased, right? Now, for example, if this was the validation accuracy. Let's try to test it on the unseen data, on the test data. So
Sorry, before you proceed, this what about the quadratic?
Yes.
Discriminant thing? It failed. What's the?
Now, who would care? Just my point.
It's just good to know, like why.
We can see this why it failed. Probably because of the different, it will give you the error as well. One or more of the classes have singular covariance matrices for their predictor values. The makes training fail. We need to see this covariance structure. We need to seek the help. Just copying and pasting this error will probably solve this issue. But this is not the goal of this research. So at the moment, for example, now if you collect the test data and your test data is in the workspace here, and I did this. So this was the validation accuracy. Now if we can test all, yes. Now the model was saved, trained model. Now we are testing it on the test data. The good thing of this tool is, for example, we can save that trained model somewhere, or we can save that entire training as a function to be called from other, yeah. This is very good point. So this tree has the test accuracy of 88.1, which is good. 88.1 also, 83, 30. Linear discriminant analysis, 98.7, Kevin. So you could click this and see, for example, you got 95.4% validation accuracy previously on the training data, and now this test accuracy is 98.7. You could save this model and you could try, for example, using this model for testing in real time. And also, like here, the good thing is you could plot, for example, confusion metrics for this model. And so here, for example, on the x-axis, here, these are false rejections. You see 4 plus 2 plus 1. So 7 samples of this class, they got falsely rejected. And 2, 1, 3 plus 1, 4, 5, 7, 8. 8 samples from other classifiers, they got mistakenly accepted as the same user, yes. So this SVM, again, they are 98.8, 98.9, 98.9. Yeah. 97.7, 97. Neural network, this support vector machine, this KNN, all of them, they are performing well. So it means our data is good. We just need to have more data. Fine. Any question? Any question, Professor Hassan?
And my questions.
Any question?
We already did a lot of questions.
Yeah, well, we were going while you are.
You are welcome. No question at all. So
Maybe some in future.
Sure. Feel free to ask anytime. Feel free to ask. You can reach me on my email if, in case you are interested to conduct research in this domain, for example, take my help, for example. I would be very, very happy to collaborate. Now I would request you on, please, now that you know the importance of this work, the results that we are already getting, please contribute to this research and participate in the experiments. Then with 10 more users, probably we will be able to publish this one. Thank you so much. If you do not have any questions. Online participants, if you have any questions. No? Okay. Good to go then.
Thank you.
I'm done, Professor.
Okay, thank you.